I have spent my life tracing lines in sand, weighing bodies in water, and searching for certainty in a world governed by uncertainty. What began as a child's curiosity beside the Sicilian shore became a lifelong pursuit of understanding, of circles and spheres, of balance and motion, of proof and principle. I was born in Syracuse on the island of Sicily in the 3rd century before the Common Era. My father, Phidias, was an astronomer, and from him I first learned to observe the heavens with discipline. Our home overlooked the harbor, where ships arrived from distant lands. The movement of vessels, the angle of sunlight, and the mechanisms crafted in workshops all stirred my curiosity. I was not drawn to what things meant in a symbolic sense. I wanted to know how they worked. Syracuse was prosperous, governed by King Hiero, who valued knowledge when it strengthened the state. The city stood between the intellectual inheritance of Greece and the expanding influence of Rome. In my youth, these tensions felt remote. My attention was fixed on geometry and the orderly relationships I sensed beneath the visible world. When I came of age, I traveled to Alexandria, the greatest center of learning of its time. There, within its vast library and among its scholars, I encountered a culture devoted to disciplined inquiry. Under the guidance of Conon of Samos, I refined my understanding of mathematics and embraced a principle that would shape my life's work. Belief is not enough. Truth requires proof. Proof is not decoration, it is structure. In Alexandria, I developed and refined the method of exhaustion, a technique of enclosing unknown quantities within known forms and narrowing uncertainty until only certainty remains. It became one of my most powerful tools. Returning to Syracuse, I divided my efforts between theoretical inquiry and practical necessity. King Hiero granted me freedom to pursue investigation, and in times of need, I offered solutions to civic problems. Among these was a device to raise water efficiently for irrigation, a helical surface enclosed within a cylinder capable of lifting water with steady rotation. It was simple in concept, but effective in application. Yet my deepest commitment was always to geometry. Machines answered immediate needs. Geometry addressed enduring questions. I devoted years to the measurement of the circle. By inscribing and circumscribing polygons with increasing numbers of sides, I narrowed the range within which the circle's true measure must lie. Through this process, I demonstrated that the area of a circle is equal to the product of its radius and its circumference. The conclusion appears concise, but it rests on patient and rigorous argument. From the circle, my attention turned to the sphere, a form defined by perfect symmetry. I compared it to the cylinder that contains it and discovered that the sphere's volume is 2/3 that of the enclosing cylinder, a ratio mirrored in their surface areas. Of all my findings, this brought me the greatest satisfaction. It expressed harmony between form and proportion with rare clarity. The spiral also commanded my interest. Generated by a line rotating at constant speed while extending outward, it revealed relationships of angle and area that demanded careful reasoning. I approached it not for utility, but because it embodied a structure worthy of understanding. Questions of balance led me to study centers of gravity. I sought to determine where bodies achieve equilibrium, recognizing that balance exposes internal structure. This inquiry extended naturally to floating bodies. Through repeated weighing and comparison, I established that an object immersed in fluid experiences an upward force equal to the weight of the fluid it displaces. This principle, derived from observation and measurement, resolved practical uncertainties and clarified the behavior of matter in water. A well-known example involved a crown commissioned for the king. Suspecting impurity in its composition, he asked for verification without damaging it. By comparing its displacement of water to that of pure gold of equal mass, I determined that the crown contained silver. The solution lay not in spectacle, but in understanding the properties of fluids. The lever provided another demonstration of proportion. By analyzing the relationship between distance and force, I showed that equilibrium depends on measurable ratios. Compound pulleys and other mechanisms followed from the same principles. To many, they appeared remarkable. To me, they were straightforward applications of geometry to force. When Rome threatened Syracuse, I was called upon to design defensive machines. Though I preferred contemplation to conflict, necessity demanded action. I developed catapults with adjustable range and mechanisms capable of destabilizing attacking ships. These devices delayed invasion, but no engineering can indefinitely withstand the momentum of empire. During the siege, I continued both defensive work and theoretical study. I understood that the resources and discipline of Rome would eventually prevail. When the city fell, I was absorbed in a geometric construction. A soldier entered and ordered me to rise. I asked that my diagram not be disturbed. The encounter ended my life abruptly. It was neither heroic nor theatrical, only the sudden conclusion of a long inquiry. Much of my work survived only in fragments. Manuscripts perish, ideas persist unevenly. Yet enough endured to influence those who followed. Mathematicians in later centuries studied my methods, tested my conclusions, and extended my reasoning. Scholars across the Mediterranean world translated, preserved, and elaborated upon the principles I set down. In medieval Europe and the Islamic world, geometry remained a language of clarity, and my arguments found new readers. During the scientific awakening of later eras, thinkers who united mathematics with observation carried forward habits of reasoning I had valued. Abstraction balanced by measurement, intuition disciplined by proof. I have been described as inventor, engineer, defender, recluse. Each contains some truth. But my primary identity was that of a mathematician seeking relationships among shapes, forces, and quantities. I made errors. I pursued lines of thought that yielded little. At times, my arguments proved difficult for others to follow. In retrospect, I would have given greater attention to communicating method as carefully as conclusion. What endures is not the machinery of war, nor the anecdotes surrounding my death. It is the disciplined search for structure beneath appearance. Each generation draws circles, studies motion, analyzes balance, and examines the properties of matter. The symbols have changed, the questions remain. Knowledge in my time depended on fragile materials and living memory. Today, preservation is stronger, yet preservation alone does not equal understanding. A proof must be traced step by step. A principle must be grasped internally. Discovery is not the artifact, but the insight it produces. Curiosity should not be confined to immediate utility. Though it often yields practical benefit, its deepest value lies in the pursuit itself. Ideas travel across languages and centuries, adapting to new tools and new minds. No discovery belongs permanently to its originator. Each thinker builds upon foundations laid by others and contributes to those yet to come. My life began beside a harbor and ended in a quiet courtyard. Between those points lay years of questioning, refinement, doubt, and satisfaction. Geometry, mechanics, astronomy, and the study of fluids are not separate pursuits, but expressions of a single impulse: to understand the world through careful reasoning. I was Archimedes of Syracuse. I questioned, reasoned, and learned. That is the measure of a life devoted to thought.